So now that we've seen that finding the equations of tangent lines to the graphs of implicit functions is really no different than finding the equations of tangent lines to the graphs of explicit functions, and that the only real difference is the manner in which you find the derivative, that's what the rest of this section is going to be about. It's going to be about specifically how to differentiate implicit functions. Now, I gave you a little bit of a preview on the previous page, but now let's break down this process a little bit more. I'm going to do one more example, and then below, down at the bottom, we're going to go through exactly what the 4 steps are. But let's start with doing one more example first so you have something in mind when we go through those steps. So we want to find the derivative of the implicit function given by this equation. So we've got y as an implicit function of x here, not as an explicit function, because you can't solve this equation for y. You could try, and it might actually be worth doing that just to convince yourself that you can't. But if you give yourself a minute or two to try to solve this for y, you'll very quickly realize that it's not possible. But this still defines y implicitly as a function of x, but just not as an explicit function. So let's look at how we can find the derivative. So we're going to start. You don't have to do this, but I'm just going to start by writing down the equation. That way my work will be immediately below it. That's something I like to do. Okay, so that's our implicit function. We're going to start by taking the derivative of both sides of the equation with respect to x. So we're going to take the derivative with respect to x of x cubed plus y cubed, and that's going to be equal to the derivative with respect to x of 6xy. And like I said on the previous page, the logic here is that if x cubed plus y cubed and 6xy are the same, then their derivatives ought to be the same as well. Okay, so now let's dive into this. So on the left-hand side, we're taking the derivative of the sum of these two terms. Well, for the x cubed part, you can think of that as an explicit portion of the left-hand side. This is entirely dependent on x. So when we take the derivative with respect to x of x cubed, it's the same as if we were just taking the derivative of an explicit function that happened to be of the form x cubed. Just use the power rule. So you're going to get 3x squared for the first term. Now for the y cubed term, that's the one you have to handle a little bit more carefully. We're not taking the derivative with respect to y, we're taking the derivative with respect to x. And y itself is a function of x. It's an implicit function, but it's still a function in the sense of having the chain rule kick in here. So we've got y as our inside function. So we're going to treat it like an inside function and do the chain rule on the second term. So we're going to get 3y squared, and that's the chain rule in action here. And then, well, remember that's only part of the chain rule. We still have to multiply by the derivative of the inside function. And if the inside function is y, well, then we're going to have to just write y prime. That's the derivative of the inside function. Okay, so that's the left-hand side. Now, the right-hand side, well, what do we have? We have 6 times x times y. It might be useful to think of this as the product of x and y, because that's really what it is, right? It's a product of two factors. Pardon me, not x, y, product of 6x and y, right? Those are the two factors. If you multiply 6x and y, you get what's exactly inside the square bracket. So this is really going to be a product rule. So let's write the product rule out carefully. We're going to have the derivative of the first factor, which is 6x, multiplied by the second factor, unchanged. Then we're going to add on 6x, unchanged, multiplied by the second factor with its derivative taken. So I'm just writing out the product rule, and I really haven't even paid attention to the fact that I have an implicit function, and that's okay because once I go to the next step, that's when that's going to come into play. But really just use the product rule with the fact that you're taking the derivative of the product of 6x and y. So you see that implicit differentiation follows all the same rules as when you're taking the derivative of explicit functions. You still are going to use the product rule and quotient rule. You're still going to use the power rule and the chain rule. And the same with exponential functions, trig functions, logarithmic functions. All those rules are still going to be in effect. It's just that when you encounter a y variable, you have to treat it like an inside function and use the chain rule. So this is really the major part of implicit differentiation here. Although it's going to show up a little bit on this term too, because when we go to take the derivative of y, we're going to do exactly what we did here and just use the y prime symbol. So I'll write one more line out here to clean this up. We're going to get 3 x squared plus 3y squared y prime. Okay, and on the right-hand side, so 6x, derivative of 6x, this has no y's in it, so just treat it like an ordinary derivative. Derivative of 6x is going to be 6. So you'll have 6y plus 6x, and then for the derivative of y, let's just put y prime, because what else can you do? Okay, so that's, now the differentiation step is complete, but we still want to find y prime. We don't, I mean, this almost looks like a big mess. We got a couple of y primes floating around in this equation, but we really want to find what y prime is. Well, so what we're going to do is we're going to solve for it. So once you get to this stage where all the differentiation is done, you want to get y prime by itself. So notice that you've got a whole bunch of terms here. We've got 4 terms in total, and each one of those terms has the property that it either has y prime as a factor or it doesn't have y prime as a factor. So just simply move all the ones that do have y prime as a factor onto one side of the equation. I like to do it onto the left side. And then all the terms that do not have y prime as a factor, move them over to the other side of the equation. I like to move them over to the right-hand side. So 3x squared, I'm going to subtract that over to the other side of the equation, and then the 6xy prime, I'm going to subtract that over to this side of the equation. So what you'll get is 3y squared y prime minus 6xy prime. And that is equal to, on the right-hand side, we'll have 6y minus 3x squared. Okay, so this guy got moved over here, and this term got moved over here. And that's what that brings us to this point. And now the reason you do this is because now everything on the left-hand side has y prime as a factor. So you have a common factor of y prime, which we can factor out. And that's what's going to allow us to actually solve for y prime. So I'm going to factor out a y prime, and I'm going to be left with 3y squared, because the first term will have 3y squared left. The second term, I'll have 6x left. Right? So I got minus 6x. And on the right-hand side, I've got 6y minus 3x squared. All right, and then now, because I factored out the y prime, now to solve for y prime, because that's going to be the final step here, is to solve for y prime, I can just divide both sides of the equation by this expression here in brackets, 3y squared minus 6x. So I'm out of room here, so how about I just cut the page in half here, and I'll carry on up here. So we have y prime is equal to, well, we'll have 6y minus 3x squared divided by 3y squared minus 6x. All right, so that is our y prime. That's how we have y prime in the end. So it's kind of like you're indirectly finding the derivative by using algebra and reasoning about it using the rules of differentiation. But you don't calculate its derivative directly because you don't actually have an explicit representation for the function. So let's break down the main steps of what we did, and then we'll go back and analyze where they showed up. So the first thing, well, going over this, an implicit function y of x may be differentiated using the following steps. So we're going to lay out the 4 steps right now. So the first thing you're going to want to do is, well, what did we do first? We had the equation, and we took the derivative of both sides with respect to x. So that's what we're going to do. We're going to differentiate both sides of the equation with respect to x. That's how you start out. Or in general, whatever your variable is. You're always going to have one letter for the implicit function and one letter for the variable. So this is assuming that the implicit function is labeled as a y and the variable is labeled as an x. Okay, so that was the first thing. That showed up at this stage, right? We took the derivative of both sides of the equation. What's the next step? Well, this is really, 1 and 2 are really part of the same step. Part of doing number 1 is doing number 2, which just tells you to pay attention to the chain rule to differentiate the terms that are dependent on y. So as it says here, you use a chain rule to differentiate terms dependent on y, treating y as an abstract function. What do I mean by that? I mean up here, where we treated y as an inside function, even though we didn't know exactly what it was. We just treated it like as a function and symbolically wrote its derivative down. This is what I mean when I say treat it as an abstract function. So that's really step 2, where step 2 happened. If you want to pin that down, that's probably the best you could do is do it on this stage. What did we do next? Well, that brings us basically down to this stage. And now that was when we brought down or made the observation that some of these terms have a y prime factor and some of them don't. So we got all the ones that do together on the same side of the equation and got all the other ones together on this other side of the equation. So really, step 3 is to separate the terms that do have a y prime factor from those that don't have a y prime factor. And the reason you do that, where did we do that? We did that at this step here. The reason you do that is so on the very next step, once you do that, you can now factor out the y prime and isolate it. So step 4, the fourth step here was really, well, let me write it down first. Factor out and isolate y prime. That was really this step as well as the conclusion up here. Right here we factored out the y prime, and then here we isolated it. And then that's implicit differentiation. And what's kind of neat is that no matter what your function looks like, you're always going to follow these 4 steps. The variability occurs in the second step, in the actual details, right? But the general flow of implicit differentiation is always going to follow those 4 steps.